This is the quantum space, and welcome to Quantum Time, a journey into one of the most mysterious and transformative frontiers of modern science. Throughout history, every leap in civilization has been powered by new ways of measuring time. Sundials guided the earliest cities, mechanical clocks enabled global navigation, and atomic clocks underpinned GPS and the digital economy. Now, quantum physics is rewriting not only how we measure time, but what time itself means. In this video, we'll explore how quantum science is reshaping our understanding of time, from bold theories and remarkable experiments to the infrastructures that will define the decades ahead. Nobody doubts the importance of time. Every daily action, from financial trades to medical scans, depends on precise timing. And yet in physics, time remains one of the least understood concepts. Is it a flow, a dimension, or an emergent property of something deeper? In 2025, quantum physics began offering answers as revolutionary as they are unsettling. This series invites us to think differently, not just about clocks, but about the very fabric of reality. Newton described time as absolute ticking uniformly throughout the universe. Einstein shattered that view, showing time could stretch and contract depending on speed and gravity, merging it with space into space-time. But in quantum theory, time is awkward. It doesn't appear as a measurable observable. Instead, it lurks as an external parameter. Physicists are left with a fundamental puzzle. If the universe is quantum at its core, how does something as essential as time sit outside the framework? To tackle that puzzle, this series takes us on 3 stages of exploration. First, the theories that dare to challenge centuries of assumptions. Second, the experiments that prove these aren't just thought games, but real effects we can test and harness. And third, the infrastructures, the systems of communication, navigation, and computing that will depend on quantum time in the decades ahead. Think of it as past, present, and future, but all reimagined through a quantum lens. In quantum mechanics, everything is probabilistic. We can measure the spin of an electron or the polarization of a photon, but we can't measure time in the same way. It sits outside, like a stage on which events unfold. Relativity disagrees it, insists time is dynamic, woven into the structure of the universe itself. Reconciling these views is one of physics' deepest challenges. Solving it isn't just an intellectual exercise, it's key to building technologies that will still work once quantum mechanics and relativity collide in extreme environments, like near black holes or in quantum networks stretching into space. One radical idea, proposed by Don Page and William Wouters, is that time itself emerges from quantum entanglement. Imagine a universe without clocks. Instead, time is defined by correlations, how one entangled system changes relative to another. In this picture, there is no universal tick-tock. Instead, what we call the passage of time is really the unfolding of relationships between quantum states. This idea suggests that time is not fundamental but relational, a property that exists only when systems are compared. That challenges the very intuition that underlies everyday experience. Another challenge to our common sense comes from reversible time. In classical life, broken cups don't reassemble, and smoke doesn't flow back into the match. But in quantum experiments, researchers have shown that photons can be coaxed back into earlier states. One key tool here is the quantum switch, which allows operations to happen in an order that can effectively be reversed. At these smallest scales, the arrow of time isn't fixed. It can bend both ways. This doesn't mean we can build a time machine, but it does show that irreversibility is not a law of nature, but a property that emerges statistically at large scales. Even stranger are experiments where photons appear to leave a material before they enter it. This phenomenon, sometimes called negative group delay, does not violate relativity, but it challenges our notion of cause and effect. It's a reminder that the way time behaves in quantum systems can look alien compared to the linear progression we experience. These effects may never scale into macroscopic time travel, but they deepen the mystery. Is cause always before effect, or does quantum physics allow causality itself to be fuzzy? Some theorists propose that time itself may have multiple dimensions, much like space has length, width, and height. In this speculative framework, the single line of time we experience may be just a projection of a richer temporal structure. Think of a shadow on a wall. It shows a shape, but it's only a slice of a three-dimensional object. Whether or not this turns out to be true, it highlights how radically different the concept of time could look once quantum and relativistic theories are reconciled. Until recently, such ideas might have stayed in the realm of philosophy. But 2025 marked the year quantum time leapt from theory into the lab. From synchronizing citywide fiber networks with entangled photons to comparing optical lattice clocks across continents, the evidence is mounting. Quantum time is real, and it's becoming measurable. In Stockholm, researchers distributed entangled photons across a metropolitan fiber network. The result? Clocks synchronized with picosecond accuracy trillionths of a second. Unlike GPS signals, which can be jammed or spoofed, this entanglement-based timing is inherently tamper-resistant. No adversary can fake entanglement without being detected. This is more than precision for precision's sake. It's the foundation for secure networks, financial markets, and even defense systems that require unforgeable time. On a larger scale, 10 optical lattice clocks in 6 countries were linked, creating a global experimental network. These clocks are so precise they could measure relativistic effects from someone standing on a chair. Together, they're edging us closer to redefining the SI second. Today's atomic definition may give way to optical clocks, whose stability is measured not in millions, but billions of years. This work turns time into a verified, shared international resource, much like GPS did for navigation. In another milestone, physicists confirmed the existence of indefinite causal order. This means that 2 operations can occur with no fixed sequence. A before B and B before A simultaneously. It sounds paradoxical, but experiments show it's possible when processes are placed in superposition. This isn't just weird, it could one day speed up quantum communications and even computations, since the order of operations can be manipulated to gain advantages over classical limits. Researchers also achieved the reversal of a single photon to a previous state. Although limited to the microscopic level, it proves that engineered time reversal is possible. For quantum technologies, this is more than a curiosity. It could enable new ways to correct errors in quantum computers or to undo unwanted interactions in sensitive quantum experiments. It's another example of how controlling time at the quantum level could lead to breakthroughs in reliability and resilience. Quantum time isn't just about proving physics theories. It's rapidly becoming the hidden operating system for next-generation infrastructure. Whether in finance, navigation, or computing, time synchronization is the invisible glue, and quantum versions of it are already starting to outclass their classical counterparts. In quantum computers, a single misaligned clock cycle can turn a correctable error into an unrecoverable failure. The tighter the timing, the greater the resilience. Entanglement-based synchronization offers tamper-proof precision at the heart of computation. Think of it as a pacemaker for quantum processors. Without it, the entire system risks collapse. The future of quantum computing is unlikely to be a single giant machine. Instead, it will be distributed modular nodes working together across kilometers. Entangled clocks and secure synchronization allow these modules to operate as if they were one. It's the difference between isolated islands and a connected archipelago joined by bridges of time. The uses go far beyond quantum computing. In finance, tamper-proof timestamps ensure market integrity. In navigation, entangled clocks provide accuracy even where GPS can't reach or where signals are jammed. In communications, synchronized quantum networks can guarantee security against eavesdropping. Wherever certainty about when matters, quantum time is set to redefine the standard. As systems scale globally and into orbit, relativistic effects become unavoidable. Satellites and ground stations tick at different rates because of gravity and motion. Entangled clocks could detect and correct these distortions in real time, creating relativity-proof networks. This is the foundation for a true global quantum internet. The road ahead is ambitious but clear. Expect campus-scale deployments of quantum time networks, international standards emerging for optical clocks, and programming languages that account for causal superpositions. We'll also see relativity-aware satellite constellations, ensuring synchronization from Earth to orbit. Step by step, quantum time will move from lab to infrastructure, becoming as essential as electricity or data networks. History shows that those who master time master the future. Mechanical clocks made global trade possible. Atomic clocks enabled GPS and the digital economy. Now, quantum clocks will underpin the quantum economy from secure communications to resilient computing. In this sense, quantum time is not just science, it is strategy. Whoever leads in this domain will shape the digital and geopolitical landscape of tomorrow. Quantum time is no longer abstract philosophy. It is a measurable, controllable resource, a foundation for computing, communication, navigation, and even governance. Just as earlier civilizations rose by mastering new forms of timekeeping, ours is entering a new era where the quantum nature of time will shape our future. Thank you for joining us on this journey. This video is presented by The Quantum Space and written, edited, and produced by Crown Communications.